Hello and welcome everyone to this EDSL webinar on design optimization for BREEAM credits, Part L and heat pump sizing. My name is Salman Khan, delighted to be the host of another EDSL webinar, which are just getting more and more interesting. This is something I've been looking forward to for a while. I've never really used the GenOp tool myself on any live actual projects, and I'm really keen to see how some of these case studies that Duncan and Andrew will be presenting today pan out. And let's see if we can have a really interesting Q&A discussion. And as a reminder, you can use the Q&A panel or the chat panel in Teams to keep posting throughout the webinar, and we'll try and take as many questions as we can before the end. Let's meet our presenters from today. I will quickly hand over to Duncan and Andrew to introduce themselves. Hi, Duncan.
Hi, I'm Duncan MacArthur. I'm a software developer at EDSL. I've been working here 25 years. So, hopefully prepared something interesting for you to see today.
Yeah, I'm Andrew. I've been at EDSL for I think almost 12 years, I think 11 and a half years now. And I started in the consultancy services department and then moved to software development. So yeah, just went from using the software to developing the software and making it better.
Great, let's take a look at the agenda today. So I'm going to hand over very quickly to Andrew, who's going to introduce the EDSL software task engineering. And then Duncan will take us through an introduction to the GenOp tool, just describe what it is, how it works, what can actually be optimized and how. And then we're going to look at a couple of case studies, including heat pumps and fabric optimization for BREEAM. And then we'll take a look at the Q&A. And just as a reminder, if you signed up for this webinar, we will share the recording and a summary of the slides for you. Great, thank you. Andrew, I will hand over to you.
Thank you, Nachman. Yeah, so most of you will probably be familiar with TAS, but just to give you a brief overview of the history, it started back in the 1970s at Cranfield University off the back of the energy crisis when it was realized that designing better buildings could reduce our dependence on oil. So from there, early commercial development began in the 1980s, and it was supported by Legal in General. And then when that funding ended, EDSL was formed to carry the work forward. So we've been going for quite a long time now. And throughout that period, we've been constantly working on our simulation engine, developing it and improving it. We did some pioneering things like modeling the mixed mode buildings for the first time, modeling internal solar tracking, and then when EPCs and the Energy Performance Building Directive came along, we were one of the first softwares to lodge a commercial EPC and one of the first tools to be approved. And a big part of what's driven our evolution and constant development is the way that we work at EDSL. So we have our consultancy services team, and they sit next to the developers, and they use the software on live projects. And then the development team are getting constant feedback from the consultants. So when something's difficult, or where there's room for improvement, or if there's a new requirement, we get that feedback right away. And then we, as a developer, we put that into the software, and then they get to test those features before we do an official release. So that also means that the software is quite robust and stable, because if there are any bugs or things like that, they pick up on that. So that's why our software is quite robust, and we feel confident in saying it. And yeah, since then we've added things like daylighting, and we've added detailed HVAC modeling. And if you were part of our previous webinars, you will have seen as well that one of the latest things that we've done is we've developed our own CFD algorithms. So we've developed something called dynamic CFD, which allows us to simulate a full day's worth of data, which, as far as we're aware, hasn't been done before. And this is very tightly integrated with the rest of the software, with the building simulator. So all the boundary conditions and things like that are set off the back of the dynamic simulation. So it's quite pioneering, it's quite fast. And we don't use pressure correction like some other packages. That we've developed our own algorithms that are validated, so it means that our simulation is very stable and fast. So in this webinar, we're gonna look at TAS GenOpt. So before I pass back over to Duncan, I'll just give you a brief overview of the software itself. So TAS has a number of core applications, and you can see those in the screen here. They're the red blocks. So normally what you do is you start in the 3D modeler, which is where you define your geometry. You can, of course, import geometry from Revit, Rhino, SketchUp, etc., IDF, Energy Plus, because we've got quite a lot of integrations with other packages. And then from there, you'd export your geometry to the building simulator. The building simulator is where you add your internal gains, construction information, weather information, things like that. define your apertures, and then you'd simulate this file and you'd get your results viewer file, which contains hourly results and load information for each zone throughout the year. And then from there, you can feed that into task systems where you do your detailed HVAC modeling. And if you want to, you can also go into the CFD tool. So yeah, I mean, there's so much that you can actually analyze with TAS, but the important thing to know is that all of our core applications, they have an API, they have a programming interface. And so that basically means that anything you can do with the UI, you can automate programmatically. And this is where TAS GenOpt comes in. So we have a number of utilities that use our core applications via this API, and TAS GenOpt is one of them. And it's a optimization tool that allows you to vary parameters in the core applications and try and find an optimal result. So Duncan's going to go through that now in a bit more detail. So I'll hand back over to you, Duncan.
Okay. So yeah, it's GenOpt stands for generic optimization. So you can basically pick variables that you wish to change, and you can try and minimize the result to find the optimum solution. So there's one of the links here is to the origin of GenOpt, and there's the various manuals for it. And we've written an interface to it that uses it and works with our software, and we call that TAS GenOpt. So yeah, so you can select variables that you wish to change. So basically anything in the interface that you can edit, you could change that as a variable, and you can create a cost function that you're trying to minimize. So in the example later on, we're trying to minimize the actual financial running cost. So we're trying to get that to as close to zero as possible. And also the other example is if you sum the heating and cooling demand across the year, we're trying to minimize that as well. So various other things you could minimize.
So like CO2 output, Duncan, is that another option?
Yeah, so you could minimize on CO2, you could minimize on consumption, on demand. Yeah, you can basically do. You can minimize most things. So you can create a cost function for most things.
So it could be a combination of CO2 and cost, and you can then balance the two.
You could. I would just show the examples that I have, and I mean you could run one minimizing on cost and one minimizing on CO2, say, and see what the difference is. Or you could set, when I've run a daylighting example, I've set a floor for the daylight factor that I want, and then I've tried to minimize, the cooling consumption, but still have a daylight factor of say 2%. So you can do those sorts of things with the cost function as well. But you basically make a barrier function. So I make 2% daylight factor. To not achieve that, you'll get a very high value in the cost function. So it kind of channels the result so that the minimized value it finds will have a daylight factor of 2 in that example. So we've got a manual for this, and there's an example that rotates the building and I think minimizes the heating and cooling demand based on the orientation of the building. So that's kind of a worked example that you can follow through. And to run TAS GenOpt, you need to install Java, and after you've installed it, you need to restart the machine so that it sets up the correct paths. So you install Java and restart the machine. And we use C# scripts These are used to both set the variables and also calculate the cost function. So in this example, I'll show you here briefly, and then I'll show you the actual model. We basically have a heat pump and a gas boiler, and there's a controller here, and based on the outside temperature, it'll use the heat pump or the gas boiler. So it's currently set up at 3 degrees. So if it's 3 degrees outside or above, it will use the heat pump, and if it's below that, it will use the gas boiler. So you kind of see here we've got, day 8, hour 15. The temperature outside is 2.7 degrees, and we can see that the flow is going around here to the gas boiler, and that's providing the heating. And then it's going along this header, and then serving the heating circuit and the DHW circuit, and then returning round. And then the next hour, it's 3.4 degrees outside, so the heat pump's in operation, and the gas boiler is not used. So yeah, so that's basically this control here. We're looking at the outside temperature, and we're either using the heat pump or the gas boiler. So
sorry, Duncan, I'm guessing that's based on the fact that the heat pump has got certain efficiencies when outside temperature is at certain values. So it's better to use the heat pump when obviously you've got a beneficial, differential temperature.
Yeah, exactly. It's there's certain temperatures below which the heat pump, the performance drops off, and it might be better to use the gas boiler. So okay, and so in terms of our cost function that I'm going to show, it's based on the actual monetary cost of running the building. So associated with the boiler is obviously a fuel source, which is gas, and the heat pump, we have an electrical fuel source, and they've got certain tariffs associated with them, so certain costs per kilowatt hour. So I can minimize on the running cost, or I could look at the CO2. So again, the fuel sources have a CO2 factor associated with them, and otherwise, if you sum up the CO2, you could try and minimize based on that. And you've got the option of consumption as well. So so if I click next here, and then when we run this script in GenOps, it basically tries different set point temperatures. So it's trying 10 degrees there, 5 degrees there, and then it's coming through with these cost results, and it's trying to find the minimum cost. And based on the result of the two simulations, it'll pick another value here, and then it sees that the cost increases, so choose another value, and basically it will try and converge and find the minimum cost. So if I show you the model, so basically if I right click here and set the current project directory, I've installed Java and I've restarted the machine, and then I have my model files. So this is basically what my model looks like. So it's about I think it's 24 zones, just an office. Okay, and it's got these zones have got internal conditions associated with them. Heating and cooling loads will be calculated based on these upper and lower limit temperatures, and we've got construction information. Also the weather data here. So if I simulate that TVD file, I get this results file, and then the systems file feeds in that results file. So I have these airside systems here and these various components to this fan call unit that sits on this heating collection here. So yeah.
So that's water side, Duncan, just to confirm.
Yeah,
so you got air side versus water side, yeah?
Yeah, so these are the air side fan coil, nat vent, extract only. And then these pieces of equipment sit on the water side, which is shown here in this schematic. So it's shown in the plant room schematic. So if I have, if I double click on this gas boiler, for example, I can see its part load efficiency, so 91% efficient, and it has natural gas as a fuel source. So I have a time of use tariff on there and an emissions factor as well. And similar to that, the heat pump has its efficiency profiles. These are basically in tables. So outdoor dry bulb, water temperature, and part load. So we have basically this nominal value will be multiplied by a factor that's looked up in here. So it's not going to be 780% efficient at all conditions. That will depend on this map here. I'll find one there.
So this is manufacturer data effectively, Duncan?
Yeah, so this is manufacturer data, the performance of the heat pump based on the outside condition and the water temperature, and whether you're running it full load or part load. And then there's a similar thing on the duty. So if you see the outside temperature of -5 degrees, it's the unit will struggle to produce any heat effectively. And this is on a electrical fuel source, and this has a cost associated with it, and also an emissions factor. So these are the 2021 NCM emissions factors that I've used here. And then the other part is this controller. So if I click here, I can see that this set point is set to 3 degrees. So if I simulate here, so if I wanted to know the optimal, I could adjust the value here and go and look at the cost graph, and keep doing it effectively until I was happy. Or I can use TaskGener to vary this value here, this variable, and try and minimize the cost in the results. In the PowerPoint, these were the 2 hours that I took the screenshots for. So when the outdoor temperature is below 3 degrees, we're using the gas boiler. That's providing the heating. and when it's above, we're using the heat pump. And then the other thing to note is in the results here, if we go to the costs and then we set this to annual, that's the total annual cost for your building. So the things that we're going to retrieve using our script, we're going to retrieve this value here for our cost function, and we're going to set this set point here. So if I close this down now, and I just right click here, I set the current project directory, and then if I right click on the file, I can choose task gen opt from the context menu.
Sorry, Duncan, just to be clear, you're varying supply temperature to try and optimize the cost. So that's the total energy bill effectively.
Yeah, so I'm changing the set point of the controller to various values to use the heat pump or the boiler.
Got it.
And based on that set point, we'll have a consumption, and then each fuel source has a different tariff associated with that consumption, and then it will calculate the cost, and that's the graph that we're
Yeah, okay, so
results from.
This is the optimal temperature to minimize cost, and the temperature is where you're switching between heat pump and boiler.
Exactly, yeah. So we can define a variable here on this right hand side. So I just click add, and I can add one. And then you type in the variable name, and you set the initial value that you want to use, and then the range. So I'm looking at a range from -5 to 35 degrees, and I've just got a step of 1. That's related to the accuracy of when it's saying it's converged. And also, if you can run this in a parametric mode as well, where it would just do all the options between -5 and 35. So it'll do the 40 options there in a step of 1. So this step has 2 purposes depending on how you're using it. So yeah, and if we have a look at this script briefly, what it does, the first step it does, basically when we run these simulations, or when GenOpt runs these simulations, it will create a temporary folder in this directory. So we need to copy these files into that temporary folder. So basically here we're just copying our TBD file and putting it in, making a copy of it and putting it in the current project directory, so that we're not going to be editing our files. We're only going to be editing a copy of them. So this basically copies the TBD, the TSD, and the TPD file. And then this variable here, we're creating a TPD document object, and we're just renewing it. So that's a common step if you're going to work with any of the files through automation. Is we need a document object, and we instantiate it by renewing it, and we can open our file. So we instantiate it, and then we just call this open on that document object, and it will read in our file. And then we fix the TSD path because we've changed directories effectively. So we've just opened our systems file, and we need a variable to hold our set point temperature. So I've just put this float set point, and I've set that equal to variables and the name, variable name from here. So that will get the value. So the initial value will be 1. And then based on the simulation, the cost function back from it, the algorithm, the search algorithm, will choose another set point temperature for us. And here I'm basically just looping through the controllers in that plant room that I showed you. And I'm looking for one called heat pump controller. So I've just given it a name so it's easy to find. So I get the heat pump controller and I just set its set point to our set point variable value here. Okay. So after I've done that, I simulate the systems model. So it's going to run the simulation and then I'll be able to get the updated results. So here, this is just a way of basically retrieving the results from those graphs. So each graph you can retrieve results from it. So I'm just saying here I want annual results. So just sum them all up and give me the total. And I want them for TPD cost. So it's just the cost graph. And then I can loop through these values and I'm just summing them. So into this D cost value. Okay. And here I'm setting the total to the cost, saving the file, closing it down. And the main thing here is this D total and the result. So the result is the thing that the algorithm's trying to minimize. So my D total is this sum of all the costs, and we're just going to try and minimize based on that. So
Just curious, Duncan, is this C++? So
this is this is C sharp.
Ah, okay, thank you.
But yeah, it's very close to C++ in the syntax. Yeah, I'm trying to think. Yeah, you can specify various values you want to output. So I've added a couple here. So got the cost and the CO2 and the result. So we go on to simulate. I'm using this golden section algorithm. There's some various options here. If I did parametric, it would just run every combination between the upper and lower limit for the variable. This golden section will basically search for the optimum result. So it will minimize the number of simulations that you need to do or that need to be undertaken. So if I just click the simulate here.
So how many simulations if you were to do it parametrically? Just curiosity.
Well, there'd be 40 with the step of 1. So in this case, we're going to be doing, I think it just does 8.
Yeah, I mean, in this example, we've just got one variable, haven't we? We've just got the set point. But if we were to add multiple variables, say we had 2 or 3 different variables and each had 10 combinations, you could quite quickly end up with hundreds of different simulations. And that's why optimization is usually a better approach than the parametric approach. Because if you do the parametric approach, you have to do every single combination. And even if it's quite quick to do an individual simulation, it will take a long time. Whereas if you think back to that graph at the beginning of the presentation, that colorful one with the line, what we're doing is doing an efficient path to find the most optimum value rather than just brute force doing absolutely everything.
Yeah, and the benefit of having written a script is you can reuse the script as well.
Yeah, so optimize on different values, like not necessarily CO2 or energy, but anything pretty much.
Yeah. Yeah, and also if you needed to rerun it, because obviously various design changes will occur.
Well, say for example, the tariffs changed as well. That's another example. Or if you wanted to see what the results would be if you had a cheaper tariff of electricity at night, for example, you might end up with a slightly different result.
So it's basically it's going through editing that set point, it's running the simulation, it's retrieving the results, and then based on the result it gets, it chooses another value to enter for the set point. It takes about 6 minutes.
Sorry, Duncan. What are the 3 lines?
Yeah. So if I go to this graph display options,
I can see the set points kicked off around what 12, 10, around there somewhere.
Yeah, set point. So yeah, it's chosen the value of 10, and then 5 there. I think there was a simulation that hasn't been plotted that was at 1.
Yeah, so it is multi-threaded. So that's another reason why at the beginning of the script we don't work on our original files. So we copy them into a separate directory, just because that way we can actually work on like 3 or 4 different versions at the same time. It says there in the text assigning 4 threads to simulations. So it is multi-threaded, and it should be quicker the more cores you've got on your computer, hopefully, depending on the algorithm, of course.
Yeah. So in this graph display options, you can uncheck various things. So our cost is the same as the result, basically. I can uncheck CO2. So I think that's what we have in the PowerPoint. So it's just the set point temperature and then the annual cost.
So cost is the X.
Yes. Yeah.
Oh, yeah.
Okay, and the set point's obviously the circle. Yeah, got it. I think we need to buy you a faster PC, Duncan.
So under scripting, there's also this option where we've written some scripts for you. So you can just double click those. And then the code turns up here, and you can copy and paste that into your script. So it's like a library that we can add to over time.
Yeah, if you wanted to use this script on another project, this exact example, all you'd have to do is copy and paste the script into your own project, and then just change the file names at the beginning. And I don't think there's much else you need to do really, other than to make sure that your system's file's got a controller with the same name, heat pump controller.
Yeah, exactly. I think this should be finished.
Okay, great. So the X plot, sorry, the line with the X's on it, that's the target, and that's what you're trying to reduce.
Yeah, that's what you're trying to minimize. So you can see it overall it's reducing as it goes across the simulations. Yeah, so it's finished now. So it's given us a result. You just click this optimization results. You can see here. It's given us the total cost, and then a value of 5.29 degrees would be the optimum set point temperature. So, yeah, and to verify, I could, type that in and simulate, and I'd have all the results for that. as well. So you could edit that there and simulate the optimum result.
Duncan, while we're
Yeah.
on that particular case, there's a few questions relating to it. Should we just take them now quickly
Okay,
while it's
yeah,
fresh in everyone's head? Yeah, thank you. So I'm just working backwards. So we have a question asking, in that case, how was the source TPD created? Was it created from scratch or was it inherited from a Part L model, for example?
I made it from the wizard. I used the. So I used this project wizard, and that created all these things. And then I had a plant room here that I edited. So I used the wizard to do most of it, and then I edited and drawn the various components to create this schematic.
Okay, great. And if someone wanted this exact model just to test and follow through the way you've done it, can we share that with them? This
Yeah.
particular
So
model? Yeah.
I was going to put this on. So it's available for download. So these two projects, I was going to put them available for
Great.
download, and in the recording to the webinar. So that should go in that webinar email.
Great.
So everyone should get access to them.
Yeah. So we'll share the models and the scripts with everyone in the follow-up email. Another couple of questions related to this case study was, how did you earlier on you were showing the heat pump performance. I think Ian jumped in and asked the question if it's manufacturer's data. So the question was, how did you upload the manufacturer's data for the heat pump into task systems?
Yeah. So I took it from this import manufacturer data, but there's also a way of, if you have the information in Excel, in tables in Excel, you can write a macro to add these modifiers.
Okay.
So each one of these is a modifier, and I can add it, and it's a table, and then basically pick. You can say which axes you want on it, and then you can enter values. But it's easier, well, it's quicker to enter all these values via a macro.
Yeah. So that file option, import manufacturer data, that takes you to what?
Next is this.
Oh, okay. There's a data wizard that
data.
talks you through it. Yeah, perfect. Okay. Another question related to the heat pump was, why does a heat pump appear under natural gas fuel sources?
The heat pump it's got the electrical fuel source. I think. Yeah, so grid supplied electricity is what the heat pump's using, and then the boiler is using natural gas.
Okay, I think that question was a bit different, just about the UI maybe. No, that's great. We have a question from
Okay.
Yeah, I think it looks like a boiler because it's got flames coming out of it, but it's actually a heat pump.
Oh yeah, the icon.
Yeah. It's a heat pump. Yeah. Okay, Stuart's asking, presumably you could produce a script to determine the optimum temperature, which would optimize another key performance indicator. For example, the optimum solution to drive down carbon emissions. Can it do that?
Yeah, so you can, if I change the script here. So I have here, so instead of reading the cost graph, the financial cost graph, it reads the CO2 graph. So I've got this value d CO2. So if I put d total equal to d CO2, then and rerun it, it will optimize based on CO2. So it will choose a set point that would give the lowest CO2 value.
Okay, Perfect. Keep your questions coming. We'll try and squeeze in some more at the end. We do have another great case study on fabric optimization that I want to get to. So I'll hand back to Duncan.
Yeah, so I close that down. So this is the first example. Next example is this. So BREEAM has got this new V7 document, and one of the items is this M2.1 analysis of fabric performance. So it's basically trying to reduce the heating demand and cooling demand over the year, and the things that we want to vary are the insulation, the thermal mass, air permeability, and the solar gain. So yeah, so in this standard, it says that your model, you should benchmark that. So one of the options to benchmark it is if I use the constructions for the baseline building, ASHRAE baseline building, 2016, and then I've chosen climate zone 5 because my weather file's in Nottingham. So when I run that simulation and I get the heating and cooling demand over the year, that's the benchmark that I'm comparing against. So I'm trying to improve on that benchmark. Yeah, so trying to improve on that benchmark. Yeah, it's just saying here that using search function reduces the number of simulations required versus the parametric study. Click next here. So these are basically the results that it gives. Maybe I'll probably show that and come back to
it. So, sorry, Duncan, how many variables was that varying?
There's 4. So it's this example here. So set the current project directory. So I just show the building quickly. You can see I've got one that M2 example benchmark. So that's the one with the ASHRAE baseline constructions. And this one is the one I'm going to vary. So one of the, if I look at my external wall, so I'm using this construction for my external wall. And to make it a bit simpler for me, I've just named this material insulation. So that's the layer of insulation. And I'm going to vary the thickness of that insulation. And then I've just called this one mass, and it's basically a concrete, and I'm just going to vary the thickness of that concrete. So that's the thermal mass that I'm altering there. To change the G value, what I'm doing is I'm getting this material layer here, and then I'm adjusting the solar transmittance value. So then that affects the whole construction. So, and for the air permeability, basically using that figure to work out, to estimate an air changes per hour figure. So if I go into here, and I currently have 0.15 air changes per hour. So that's the value I'm going to be editing as well. So I've simulated that with the benchmark, and I've got the results out. And then I've just hard coded those into this script for simplicity. So the benchmark is this figure here. So I've added these 4 variables. So insulation thickness, the thermal mass thickness, my air permeability figure, and solar transmittance. So that's just solar transmittance for that one layer of glazing. And then I've set the minimum and maximum values and step sizes and an initial value. So, and this is just very similar to the previous script in that I make copies of the files and put them in the current directory. I create this document object, so I new this document object, and then I make these variables to receive the variables from here. And then I just go and set them. So I'm looping through the constructions in the building, and I'm looking for a material called insulation, and then I set that based on the insulation thickness. Yeah. And I do the same for the mass. The internal conditions, I just run through each of them, and based on the air permeability, I'm just dividing by 20 to estimate the air changes per hour. If it's this is from SIBSI Guide A, so if it's in a high wind area exposed, suggesting divide by 10. If it's sheltered, divide by 30. The other thing is, based on your air conditioning system, you might expect when that's on that the infiltration drops, and so there's lots of different options there for how you want to model the infiltration. But I've just set an air change rate, and that will be all the time for the zone. It'll just be constant. And then this final bit here is I get my some call construction, and then I find the third layer, which is the one I want to edit, and I set the solar transmittance there. And then I just have to make sure that I don't exceed the reflectance plus the absorbance plus the transmittance doesn't exceed 1. So this is kind of what this is doing here. So it's making sure the reflectance and the absorbance will sum to 1. And this bit's just retrieving the G value, so I'm not sure what G value that will give me. So I retrieve it here, and I put that as output. I then save my TVD file and simulate it, so from day 1 to 365, and create a TSD file. And here I make the TSD document, open it, and basically retrieve the results. So this is there's a function to get annual result, but it's quicker to actually go through the days and then the hours in each day, just because of the way the data is. So this is all this is doing, and I'm basically retrieving the cooling load and the heating load, and then I sum those in some CL for cooling load, some HL for heating load, and some result here. So that's the sum of the heating and cooling load for all the zones. I calculate this improvement based on the benchmark, so it just gives a percentage improvement. And then some result, I've set that here. So this is the thing that's being minimized.
That's your cost function, basically.
Yeah, that's the cost function. Yeah. And then because this is multiple variables, we need to use a different algorithm. So I'm using this Hooks-Jeeves algorithm. I mean, I can run it here, but it won't finish in time because it takes roughly 177 simulations because it's got all the various variables. So when I do run it, I get something that looks a bit like this when it's finished. So it's basically giving me these results here. So it's the thickest insulation I'd allow, and thermal mass thickness, and then permeability value of 3, which is the minimum I stated, and then a G value of 0.4. And I achieved a 23%, 24% reduction in the demand compared to the benchmark.
Yeah, so there's the graph at the top, Duncan. That's the sort of convergence process where it's sort of going through each of the various options, changing stuff.
Yeah, so I wonder if I can, if I run it, it will start filling it in. So it'll be a bit easier to see if there's only a few on there. But as I say, this might take a while. So yeah, it's basically, if I look here at the mass, it's trying a mass figure of 150 mil, and then at this point it says, well, maybe I'll try a different mass figure. So it reduces it by 0.5 mil, and then that result isn't a minimum, or the gradient's in the wrong direction, so it goes back, and then it tries again. You can kind of see that here with the insulation thickness as well. So it's stepping up. It's running the other it's keeping these the same and running the other combinations, and then it steps up again. And then
where's the cost function? Sorry, Duncan.
Yeah, so it's here, this result, and it's just coming along the bottom here to this green cross.
Oh, okay, so that's the one that's going down. Yeah, okay,
yeah,
which is good.
Green cross. Yeah. So yeah, so it's basically taking it in turns to change a variable, and then seeing what happens to that result, and then it tries to change the next variable. Yeah, so these examples will be available for download in the link in the email that we send out. So yeah, I guess the other is it's starting to plot some things. Yeah, so this is that BREEAM document section here. If I go scroll up slightly, there's this building form methodology as well. So other things that it's asking to optimize on. So you can do daylight modeling. You can try and make the floor more uniform by adjusting window positions and things like that.
Shade positions as well. Yeah.
Yeah, the position of shades, like overhangs, fins,
Number
and
of
things.
fins. Yeah.
This building orientation, that would say that in the manual, that's an example in the manual where we rotate the building to try and minimize the demand, heating and cooling demand. So there's scope for doing these types of solving these types of problems as well. That example
Sorry.
is just this.
The time's gone quite quickly today. We've got about 5-6 minutes left. If you want to save some time for questions as well.
Okay, so yeah, so that's basically those two examples. We offer EDSL offer consultancy services as well. So Part L, EPC assessments, comfort analysis, energy modeling, heat load sizing, various other things. So if we offer a consultancy service using TAS as well. So and yeah, any questions really?
Let's squeeze in a couple more questions. We have a few minutes left. So, Duncan, I know this is one of your favorite questions. So we have a couple of people who've asked on posting questions privately about Part L, right? So what would be where would you start with that using optimization for Part L? What's your opinion there?
I think because Part L, there's a lot of rules around Part L. I would try and optimize my design, and then I'd put that design into Part L, and you should see a better result, improvement that way, as opposed to trying to actually optimize for Part L itself. Yeah, because lots of things, there's various rules for the notional building. You're trying to beat the notional, so a lot of time you're saying, well, the notional uses demand control, so if I'm going to reduce my auxiliary energy, I need to use demand control. So I would do that first in the studio, and then I would work on my design outside of Part L if I was going to optimize anything.
Andrew, anything to add there?
No, I think that's a good approach, really, because Part L is it's got quite a lot of rules to it. So a good building design should be independent of Part L, really. So it's always a good starting point to start there.
Okay, two related questions. One is GenOpt for projects, right? So users who are interested in trying out GenOpt, but they might not be, coders or good at, C# or C++. What's a good way to get started with these scripts that you've shared, the ones you showed and the ones you showed on the menu? And second, does your consulting service include, GenOpt, helping companies set up a GenOpt script and possibly training?
Yeah, so we do offer it as a consultancy service, and normally what we do is if you come to us with a problem, we will, if you want us to do the full script for you, we can, and then we leave lots of comments and things and explain how it works so you can make changes to it and use it on other projects. But alternatively, if you do have a go at doing GenOps scripts yourself and you run into some trouble, you can always email support, and we'll be able to help you with any difficulties you might encounter. And it might seem like it's quite intimidating to write a GenOps script, especially if you're not familiar with coding, because there's quite a lot of complex syntax and things like that when you first see it. But what we usually do is we split up all the things that a script does into lots of small functions, and you can understand what each chunk does just by reading the name of it. So it's a little bit like visual programming. You can just take a series of these small functions and string them together to achieve what you want. So in reality, you shouldn't really need to write that much code yourself. You can just use our script library and start from there and take lots of little small examples that we've written and put them together.
Okay, great. So Sam and other people who said yes to that question, we'll summarize this kind of easy steps to get started with scripts and the sample scripts in the follow-up email we're going to send by end of this week. Last question from Caitlin. This is a great question. Can you only optimize the result value to the minimum, or can you set a goal value for the result? For instance, can it be used to vary boiler efficiency / infiltration to match known gas consumption for an existing building?
I mean, you can, if you're trying to target a value other than 0, I mean, it will just try and minimize to 0.
We actually did this. So we wrote a script for one of our customers to assist them to basically do essentially this, but we did it with outside air temperature. So basically, the internal temperature of a real building. So we did a calibrated energy model where we measured data for the inside of a space, and we wanted to vary the crack parameter to vary infiltration in order to match up with measured data. So rather than like minimizing the cost function, just setting it generic, minimized to 0, what we did is we took the difference between the simulated internal temperature and the measured internal temperature, sum that together, and then minimize that. So you can actually form that question, trying to match, what did you say, the gas consumption, the known gas consumption. You can formulate that in such a way that if you minimize that value, you end up with a really, really good match. So it can be done, yeah.
Fantastic. We're on top of the hour. We do have a couple of other questions, but we should finish there. It's been the full hour already. It shows the depth and breadth of questions there. We will follow up with questions we couldn't take in the follow-up email. Thank you everyone for joining. I'll hand over to Duncan for some closing remarks on this one, Duncan, since you put a lot of this together and we appreciate that. Okay, there's a lot of interest here, Duncan, so we'll be following up with people a few times.
I was supposed to be picking this one up, by the way, Duncan. But thank you. No. Go, Duncan. Yeah. Great presentation. Thoroughly enjoyed that. Thank you, Duncan.
Yeah, thanks for your interest, and just contact us at support@edsl.net if you have any, follow-up questions or you need any help with anything. We'll do our best to help you. So.
Thanks very much.
Thanks very much.
No, thank you, Nagman, for hosting and doing the intro and the outro. So yeah, excellent. Nice work. Good job, everyone.